Welcome everyone to the Prakash Academy virtual classroom. I am absolutely thrilled to have you joining me today. Get ready, because for today's explainer, we're going to master one of the most foundational, mind-bending, and honestly fascinating concepts in all of organic chemistry, isomerism. If you've ever wondered how nature can take the exact same set of chemical building blocks and create completely different substances, well, you are definitely in the right place. Let's jump right in.
Okay, let's dive into this by picturing something we see every single day. Imagine two totally different houses built with exactly the same number and type of bricks. Just think about that for a second. You've got a pile of red bricks, some wooden beams, and glass windows. A master builder could take that exact same pile and build a towering, narrow townhouse, right? Or they could take those very same materials and build a wide, single-story ranch home. The raw materials are identical, but the final structures, their shapes, and how you actually interact with them are completely different. In organic chemistry, this is exactly what happens with atoms. It's the absolute perfect way to visualize our topic for today.
So here's our roadmap for today's explainer. We'll start with a quick welcome to the Academy, define what isomerism actually is, take some deep dives into both chain and position isomerism, explore functional groups, and finally, wrap up with a quick revision and some key facts. Section 1. Welcome to Prakash Academy, setting the foundation. Let's get right to the core concept.
Section 2. What is isomerism? Unlocking the chemical twins.
So, what are isomers? Basically, they're compounds that have the exact same molecular formula. That means if you count up all the carbon, hydrogen, or oxygen atoms, the total tally is completely identical. But here's the catch. They have different structural formula. This means the way those atoms are arranged, how they're physically connected to one another in 3D space is entirely different. This phenomenon is called isomerism, effectively turning molecules into what we might call chemical twins. They share the same genetic makeup, so to speak, but they look and act completely differently. The crucial point here really comes down to these key characteristics. Number 1, same molecular formula. The atom count has to be identical. Number 2, different structures. The connectivity is changed up, but number 3 is where it gets absolutely crucial for your exams and for real-world chemistry. Because they have different structures, they end up with different physical properties. We're talking about things like boiling points, melting points, and density. And they often have different chemical properties too, meaning they react differently when you mix them with other substances. Even though their chemical formula is a perfect match, their structural differences give them entirely unique personalities.
Section 3. Deep dive into chain isomerism, where the skeleton changes. Let's take a much closer look at this first main category of structural isomerism. This is where the big difference lies in the fundamental way the carbon atoms connect to each other.
Chain isomerism, which you might sometimes hear called nuclear or skeletal isomerism, happens when the actual carbon chain itself changes shape. Think of the carbon atoms as the spine or the skeleton of the molecule. In chain isomerism, we're changing whether that spine is just one long continuous straight line or whether it branches out in different directions, kind of like a tree.
Check out how brilliantly this illustrates exactly what we're talking about. Both of these molecules have the molecular formula C4H10, 4 carbons, 10 hydrogens. Now, for N-butane, notice how those 4 carbons are linked in a single, continuous straight row. But then look at isobutane, also known as 2-methylpropane. We still have 4 carbons, but now there's a central carbon with 3 other carbons branching right off of it. It's the exact same formula, C4H10, but because one is a straight line and the other is a branch structure, they are chain isomers. And why does this matter in the real world? Well, a straight chain like N-butane has a larger surface area, meaning the molecules pack together tightly, which actually gives it a higher boiling point. Isobutane, being branched and compact almost like a sphere, has less surface area, less attraction to its neighbors, and a lower boiling point. The skeleton literally dictates the physical reality.
Now, what's really interesting here is the number 3. Why 3? Because as we add more carbon atoms, the possibilities just multiply. If we move from butane, which has 4 carbons, up to pentane, which has 5 carbons, and the formula C5H12, nature can suddenly form 3 different chain isomers. We get N-pentane, which is a straight chain of 5, isopentane, which has a single branch, and neopentane, which looks almost like a plus sign with a central carbon surrounded by 4 others. It goes right back to our analogy. The more bricks you have, the more different houses you can build.
Section 4. Deep dive into position isomerism. Location, location, location. Here the underlying carbon skeleton stays exactly the same, but the action moves. So in position isomerism, we aren't bending the skeleton anymore, we're not making it branched instead of straight, the carbon chain remains totally identical. Instead, we are just changing the location, the address, if you will, of a specific chemical feature. That feature could be a functional group, or it could be a double or triple bond. We're just sliding that special feature down the carbon chain to a new spot. And by changing its location, we completely alter how this molecule might bump into and react with other chemicals in its environment.
Let's look at this in action. Listen closely to the names here. Both of these molecules are butene, with the formula C4H8. The carbon skeleton is just 4 carbons in a row for both. But in but1-ene, that number 1 tells us the double bond is located right at the start, between carbon 1 and carbon 2. Now consider but2-ene. That double bond has shifted inwards. It's now positioned between carbon 2 and carbon 3. We didn't change the skeleton, we just changed the position of the double bond. That is position isomerism. And by shifting that reactive double bond into the center of the molecule, it becomes slightly more protected from its surroundings, which can actually alter how quickly it reacts with other substances. And this applies perfectly to functional groups too. Propan-1-ol and propan-2-ol both share the exact same formula, C3H8O. Both have a 3-carbon straight chain, but the alcohol group, the OH group, changes its address. In propan-1-ol, it's attached to the very end of the chain, on carbon 1. It's wide open, highly accessible to other molecules. But in propan-2-ol, that functional group jumps positions and attaches to the middle carbon, carbon 2. This creates what chemists call steric hindrance. Basically, the functional group is more crowded by the neighboring carbon atoms. This shift in location means these two twins will behave totally differently when exposed to chemical reagents. Same skeleton, new location, totally different behavior.
Section 5. Functional group isomerism. Different chemical families. Now, we're encountering a type of structural isomerism that completely rewrites the core identity of the compound.
Functional group isomerism features the exact same molecular formula, but the atoms rearrange themselves in such a radical way that they form entirely different functional groups. This is a massive shift, guys. It means the same raw atoms can assemble into completely different chemical families that have radically different properties and uses.
Here is a totally classic example. Both of these molecules share the exact same formula, C2H6O. But look at what happens. In the first arrangement, those atoms form ethanol. The oxygen is bonded to a hydrogen, creating an alcohol group. Ethanol is a liquid at room temperature. It's the type of alcohol found in beverages. But if you take those exact same 2 carbons, 6 hydrogens, and 1 oxygen and rearrange them into our second structure, wow! Now the oxygen is sandwiched right in the middle between the 2 carbons. This forms dimethyl ether. It's no longer an alcohol at all. It belongs to the ether family. Dimethyl ether is actually a gas at room temperature and is used as an aerosol propellant. Same exact formula, 2 vastly different substances, all because of the functional group. Section 6. Quick revision and facts. Let's lock in some memory tips. To wrap up our explainer today, we're going to quickly review what we've learned so you can confidently ace your exams on this topic.
First up, a really easy memory tip. Always remember our chemical twin analogy. Just like identical twins might look exactly the same at a quick glance, isomers look identical on paper as a molecular formula. But, just like twins have entirely different personalities, hobbies, and behaviors, isomers behave uniquely in the real world when it comes to their physical and chemical properties. Next, keep this simple rule in mind. More carbon atoms equal more possible isomers. The possibilities scale up incredibly fast. Remember earlier we said butane, with 4 carbons, has 2 isomers, and pentane, with 5 carbons, has 3? Well, hexane, for instance, represents 5 different structural possibilities. By just adding 1 single carbon to make a 6-carbon chain, the complexity jumps, and it literally just keeps growing exponentially from there.
This cheat sheet perfectly summarizes the 3 types of structural isomerism we covered today. For chain isomerism, remember the difference is the carbon skeleton itself, straight versus branched, like N-butane and isobutane. For position isomerism, the difference is the location of the group or bond, like sliding that double bond from but1-ene to but2-ene. And for functional group isomerism, the difference is entirely different functional groups, like turning an alcohol into an ether with ethanol and dimethyl ether. Definitely keep these classic examples in your back pocket.
As we close our session at the Prakash Academy virtual classroom today, I want to leave you with a bit of a provocative question to chew on.
If larger carbon chains keep growing the number of chemical twins, is there a limit to how many structural personalities a single molecular formula can have? Just consider how complex these chains can get. When you get up to organic molecules with 20, 30, or 40 carbon atoms, the number of possible isomers rockets into the billions. It truly shows how the possibilities of these molecular building blocks are virtually infinite. Thank you so much for exploring isomerism with me today, and keep questioning the incredible structural world all around you.